Today's lesson is on vectors, and we're really going to do just a pretty superficial probe into vectors. You'll use vectors a whole lot more when you get into pre-calc and calculus. So this is just kind of going to whet your appetite for it. So what is a vector? A vector is any quantity with, with magnitude. I don't know what went wrong there a second ago. Magnitude, which relates to its size, and direction. Vector has magnitude and direction. Okay, and we have notation that we use for a vector. It's similar to the notation for a ray. For example, ray xy, and this might be hard to see, so I'm going to write it a little bit larger over here. Ray xy, we know we use this symbology there for it. So if I'm talking about vector xy, I still put my XY and I put my arrow on the top, but the arrow just has one side. You can see it just has this one side here, not the full arrow like on the ray. Okay, so make sure you know that notation. Suppose we have vector KW or KW like we see here, and here's that vector in our picture. This is vector KW. The magnitude corresponds to the distance from the initial point K, which you see in our picture here is right there, initial point K, to the terminal point W. The terminal point is always going to be the end that has the arrow on it, and the direction corresponds to the direction in which the arrow points. So there's an illustration of how we could use a vector. We'll get much more in detail here in a minute so you can see what we're really going to use this for. You can also use an ordered pair, x and y, with an x component and a y component in the coordinate plane for a vector. But you see here we use these little brackets around the x and y when we're using vector notation instead of parentheses when we're just talking about coordinates. The magnitude and direction of the vector correspond to the distance and direction of x and y from the origin. Okay, so let's go over here and look at some examples. What is vector OL, right? This is vector OL. We can see from our symbology, vector OL, which we know is written like that, vector OL. What is it as an ordered pair? And it says round to the nearest tenth. Okay, well, when I want it as an ordered pair, remember I need an x component and a y component. So I've got to figure out, look here, here's my x component, here's my y component, and the red is the vector itself. Okay, the red is the vector itself. So how can I find out what the x and y components are? Well, I know the angle measure associated with that vector. I know the magnitude of the vector is 65. So, I think I got to use trig here, right? And I know that related to the 50 degrees, x is the side adjacent. So I'm going to say cosine 50 equals side adjacent over hypotenuse. So x is going to be 65 cosine 50. And it said round to the nearest tenth, so we're going to do that. Let's go over here and grab our calculator. Hope you got your calculator out. So 65 cosine 50. Make sure you're in degree mode. Let me check it out. Make sure I'm in degree mode. I am in degree mode. So now I'm going to do 65 cosine 50. Close my parentheses. And so 41.8, that's going to be rounded to the nearest tenth. 41.8. Okay, now let's get the y. We're going to use sine, right? Because y is opposite the 50-degree angle. So sine of 50 equals y over 65. So 65 sine 50 equals y, and that's going to be approximately 65 sine 50, and that's going to be about 49.8. 49.8. Okay, and now we want to come up here, we want to put this in our vector notation, so let's see what it's going to be. OL as an ordered pair is going to be, x is 41.8. But what about the y component, guys? You see I'm going in the negative direction for the y component, so I've got to put a negative number in there. So that's going to be negative 49.8, and that's going to be my vector represented in vector notation as an ordered pair. All right. Let's do another one. Express the vector below. Okay, same kind of situation. The vector is the hypotenuse. Okay, let's look at what we have here. We have our x is going in the negative direction, our y is going in the negative direction. So we know they're both going to be negative numbers, right? We're going to use our trig. Okay, here's x, here's y. We're going to use cosine again. So cosine of 10 equals x over 3/12. So x equals, and I've already worked this out, so I'm not going to go to the calculator this time. I'm just going to tell you that it comes out to be approximately 307.3. X is 312 times the cosine of 10. You can punch that in, and you really need to do that. Okay, and how about y here is side opposite, so we're going to use sine. The sine of 10 is y over 312. So y is 312 sine 10. So y is approximately 54.2. And of course, when I write that in vector notation, as we said earlier, they're both going to be negative because the x is going to the left, the y is going down. They're both negative. So I got negative 307.3, negative 54.2. That's how we find the components of a vector using trig. Okay? In many vector applications, you'll need to describe the direction of a vector. For instance, if I look at this vector here, okay, I can see this is due east, right? And I'm going a little bit south of that. This vector would be 25 degrees south of east. That's how we would describe the direction of that vector. This one here would be 35 degrees east of north. Okay, so we're going to want to describe the magnitude and the direction of our vectors. All right, what is the direction of the vector below? Is there more than one way we could describe this? Okay, well, my first instinct is to say, okay, well, it's 60 degrees, and I'm going south of west. But look, this angle right here would be 30 degrees, right? So I could also say 30 degrees west of south, right? 30 degrees west of south, same thing. We just typically describe the direction of our vectors with respect to east and west, but that's not to say that we couldn't do it another way. All right, now we want to find out how to find the magnitude and direction of a vector. So let's take this problem. An airplane lands, I'm going to draw myself a sketch over here. Airplane lands 40 kilometers west and 25 kilometers south from where it took off. Okay, so let's assume it's taking off here. That'll be our origin, and it lands 40 kilometers west. So I'm going to come this direction, 40, right? 40 kilometers west and 25 kilometers south. Okay, that's 25. Can't really see that too well. And so this is going to be our vector right there. 40 kilometers west, 25 kilometers south. So use vector notation to describe the trip. Okay, so I'm just going to call that a P. That's our plane trip. There's my vector. And the vector notation, of course, is going to be, if I'm going west, that's going to be negative 40, and I'm going south, negative 25. So there's my vector notation to describe the trip. What are the approximate magnitude and direction of the flight? Okay, well the magnitude, of course, is going to be the hypotenuse of this right triangle that I've set up here. Right, I got a right triangle. The vector, the magnitude is always going to be the hypotenuse. Okay, so how do we find the hypotenuse? Oh, we use the Pythagorean theorem, and we denote the magnitude by putting what looks like absolute value signs around that vector. And so what we got to do is we got to take negative 40 squared plus negative 25 squared, and that's going to be our magnitude. And when we type that into our calculator, and let's see, it doesn't tell us what to round to, so let's just round to the nearest tenth. That's going to be about 47.2 kilometers. That's the magnitude of our vector that is representing that airplane flight. Okay, and that is describing his distance, not his speed. All right, and how about direction? How are we going to find the direction? Let me draw this a little bit bigger here. So there's our vector. Okay, and we just said that's about 47.2. This is 40. This is 25. So this is the angle I need right here. I'm going to highlight it in red. This is the angle I need, right? That's the angle I need right there. How am I going to find that? Oh, well, I've got all the side lengths of my triangle, so why don't I use the tangent? I've got the side opposite. I've got the side adjacent. So I'm going to say tangent of whatever that angle is, we'll just call it A for the moment, is the side opposite over side adjacent, which is 40. So that means the inverse tangent, I'm going to go ahead and simplify 25/40 for a little bit. A little bit. So let's see, 5, we're going to that 5/8. And that's going to equal our angle. So our angle measure is going to be, let's go grab our calculator and do that inverse tangent of 5/8. Inverse tangent 5 divided by 8. And that's going to give us about 32 degrees. 32 degrees. And we need to put the direction on there. So what is that direction going to be? That's going to be south of west, right? South of west. So there's the vector that describes the flight of this airplane. It's going about, its flight is represented by the vector 47.2 kilometers and at a direction of 32 degrees south of west. Okay, here's one for you to practice. So just pause right here. I'll put it up and you can come back and check. All right, so of course we always want to draw ourselves a sketch so we can see what's going on. Our plane lands 246 miles east and 76 miles north of where it took off. So we sketch that in. You see I drew my 246 east, my 76 north, which makes my vector for the plane the hypotenuse of that right triangle. Once again, always going to be the case. And so here's my vector notation. Since I'm going east and north, both of my components are going to be positive. When I want to find the magnitude of the vector, of course I use the Pythagorean theorem, and I know that hypotenuse is going to be the square root of the sum of the squares of the other two legs of the triangle, and that's going to give me about 257.5 miles. And then to find the direction of the vector, I'm going to use tangent again because I got the side opposite and the side adjacent, and when I punch that into my calculator, I get about 17.2 degrees north of east, the vector describing the flight of that airplane. Okay, now, what if we want to add vectors? The sum of two vectors is known as the resultant vector. When you add two vectors, you can add two vectors simply by adding their components. It's not difficult at all to add vectors. As you can see, if I've got two vectors represented in vector notation here, I just add the x coordinates, add the y coordinates, and then I've got my resultant vector. Okay, so here's a little example. Vectors A and C are shown at the right. A is -4, -3. C is 1, -2. What is the resultant E? Okay, well, E is going to be -4 plus 1, comma, -3 plus -2. So E is going to be -3, -5. So if I were to sketch in the resultant, 1, 2, 3, 1, 2, 3, 4, 5, that would be the resultant right there. Okay, easy as that. Add the components to find the resultant. What is the resultant of these two vectors? So it says let's draw a sketch. Okay, let's draw a sketch first. We got 2, 3. So 2, 3. So there's our first one. 2, 3. And then we got -4, -2. So -4, -2. So there's our other one, -4, -2. And then we want to know what is the resultant. So I'm going to just call it R. Let me do it a different color. We'll make it green. R, I'm just going to add the components. 2 plus -4, 3 plus -2. And that's going to be -2, 1. And if I sketch that in, -2, 1, there's going to be my resultant vector right there, the green one, -2, 1. Okay, so it says, what is a real-life scenario for using vector sums? Well, I'm just going to show you in an example problem below. All right, your friend advised you to go boating with him on the river. Excellent. The speed of the powerboat in still water is 35 miles per hour. So, of course, we need a sketch. And it says the river flows directly south at 8 miles per hour. The powerboat heads directly west. So I'm going to sketch in my boat here. My boat heads west at 35 miles per hour. 35. The river flows directly south at 8. So I'm just going to put that right on the tail end here. There's 8. Okay. The river is acting on the boat. The boat's trying to go due west, and the water, I can't think of the word I'm trying to say. Anyway, the water is pushing the boat. Okay, so we want to find the resultant. And that's going to be here, of course. That's going to be the vector that actually represents. So let's do this. Let's take the boat. Let's call it B vector, and we want to put it in component form. What's it going to be? It's going to be -35, 0. It's got no y component. Okay, and then let's call the water W. All right, and it's going directly south, so we're going to call it 0, -8. It's got no x component. So when I add those two together, we'll call that the resultant. Okay, it's going to be -35, -8, right? -35, -8. Okay, well, we want the magnitude. The resultant speed would be the magnitude. So let's go find the magnitude of our resultant vector. That's going to be the square root of -35 squared plus -8 squared. So the resultant speed is going to be approximately 35.9 miles per hour. So that water is actually causing the boat to go faster, right? All right, and then we want the direction, right? We want the direction, which is going to be our angle right here. All right, so what are we going to do? Once again, we're going to use tangent because we've got the side opposite. We also have the hypotenuse now, but we don't want to use a rounded off figure, so we're going to stick with tangent. So I know that I'm going to need the inverse tangent of the side opposite over the side adjacent. And that's going to be the measure of our angle. And so A, and I don't know why I'm calling it A, you can call it anything you want to. So that's going to be approximately 12.9 degrees, and let's see, what is that? Looks like south of west, right? South of west, because that water is bearing down on that boat, making it go a little bit off course, south of west. Okay, let's see what else we got. One more problem. Okay, this one is pretty challenging. I would like for you to give it a try. I'm not going to put it up yet, so you give it a try, and then we will go over it first thing when we get to class tomorrow. See you then.